Hey everyone, we're doing Codeforces Round 891 today. It took a while to load these problems. How does this work? Let's see. 2000. Okay, I think we're just going... Oh, these are strings. Right, that's fine. If the number is a 5 or more, you just bump up the next number. Okay, so... Oh, I need to... the increment is annoying. Like 995. Not zero, character zero. Oh, everything afterward becomes 0. This was a very bad start. Go back to A. Oh, A's just... is the sum even? Oh, that's not quite right. Or is that right? Wait, no, it's just, yeah. Oh, that's terrible. Man, I could have done this earlier. It's a very poor choice then. Any, okay, so any, right, that means that's fine, that's pretty straightforward. That's kind of hilarious. Oh, this is more like, well, Wait, sorry. AU minus BU is going to AV minus BU is going. Oh, okay. This is some very basic. Oh, this stopped working. It seems like it matches, just that. Wait, what? It's just the sum of the lengths of the intervals? Four, 1, 2. 3, 2, 1. Okay. Oops, I don't want to deal with overflow. That'll be great. Okay. That is a very bad. What is that starch? How does geothermal even open the problems at the beginning of the contest? AI plus AJ plus X and AI times AJ plus Y. That means AI and AJ are kind of defined. So we just okay. Yes. So Yes. Oh, I see. Oh, I see. So I see. So for every non-tree pair, you can put an edge that's greater than the path max. You need to like break it down by path max. I see. Okay, so I can just do this with like crystals. Kind of like a crystals, yeah. I wanted. Right, so, oh, yeah, so for all of these pairs, except for one. The number of weights you can make is S minus W Oh, I... One, ah, come on. Oh. Oh, I guess it doesn't really matter in terms of timing. Okay, so just want to make sure I don't overflow anything. Wait, 85? That is bad. I think this guy will pass me, but that's it. Okay, cool. Anyway, top 3 for now, maybe 4th. It's tied, that's pretty funny. Cool. I'll be back to talk about these problems. All right. Contest is nearly over. Sitting in 4th place. Let's walk through some quick explanations to these problems. All right, so problem A, we want to know, can we color all the elements in 2 colors where the sum of the elements of both colors have the same parity and each color has at least 1 element? This turns out to be really simple. This is actually just, is the sum of the array even? Because if the sum of the array is odd, then you cannot do it. If you split it into 2 parts, one will be even, one will be odd. And if it's even, you can split it any way that you want, and the parity will be the same because the total sum is even. And since n is at least 2, we can always split it in a way where we color both colors. So code is super simple. I use the accumulate function to add everything up, check if that's even, and then that's it. Problem B. This problem is a little weird. The explanation is very complicated, but you're just rounding the number up wherever you can and then seeing what you can do. In this case, the simple greedy works. You just go from right to left and round up if it's available, and then just repeat from the right end to the left. And so that's what we do here. We add a 0 just so that we can, you know, if the number starts with a 9, we can add an extra digit in the front if we need it, and then we might get rid of it later. Take the size, and so just go. If it's at least 5, we can round up. So we set this to 0, and we're trying to increment the previous number. Remember that starting from here, we'll have to set everything to 0 afterward. And then we just do a quick loop to set all the, if there are a bunch of 9s in a row, set them all to 0. And then finally increment a digit. And that's why we need this 0, just in case this goes past the beginning of the input. And then afterward, just remember to set to 0. Remove the 0 at the front if you need to remove it, and then output. So that's B. Problem C, yes. We're taking the minimum of every pair. We get that array, and we need to reconstruct the original. So just a quick example should actually be very illustrative for this problem. Let's do the pair minimums of this array. So we have 1, 2 gives us 1, 1, 3 gives us 1, 1, 4 gives us 1, 2, 3 is 2, 2, 4 is 2, and 3, 4 is 3. And in general, it will look like this. If we have 1, 2, 3, 4, 5, for example, it'll just be 1, 1, 1, 1, 1, or yeah, like that. And so it's pretty clear what to do now. If we just sort our array, we take the first one, and we jump by n minus 1, we take this one, jump by n minus 2, we take this one, jump by n minus 3, we take this one, and so on. The only thing is, notice that we'll never actually get this value in the pair minimums array. And so what I actually do is I just do 1, 2, 3, 4, and then I put another 4. Because that would generate the same array here. So yeah, that's it for C in terms of the logic. So yeah, we just input, sort it, take the number, jump by this amount, decrement the jump. By the end, we'll have n minus 1 numbers, and then we just add the last number again. Output that. That's C. Problem D. Oh, this one is a little silly. You have this constraint, right? Basically, AU minus AV is greater than to BU minus BV. So we just rearrange this. AU minus BU is greater than to AV minus BV. And now it's very obvious what's going on. We just sort them by AU minus BU. And then as long as this holds, you'll have an edge that way. You want to know who can reach everybody. It's just the vertices with the max value of AU minus BU. And that's what we do in the code. So we go in here. If AI minus BI is a new max, we take that and we take just I as the indices. Otherwise, if it's equal, we add it to the indices. Then we just output all the indices. So yeah, that's D. Problem E. Right, so we just need to decipher what does this mean, these segments. The power is the number of segments that intersect the point. If you sum up the powers for every coordinate, you're actually just summing up the lengths of every segment. Okay, and so now we're just saying for every xi, what is the length, the sum of the lengths of every segment where it's xi and xj basically, over all j. And to do that, this is a pretty standard idea. You take the x values, sort them, take the prefix sums, and so you're just kind of binary searching for your current x value, finding where that is in the sorted array. And then you need x minus xi for the xi that's less than x. Basically you have x1, x2, x3, you have your current x, x4, x5, and you're kind of adding up x minus x1, right? X minus x2, but then x4 minus x, and x5 minus x, right? It's almost this, you need to add 1 to each of these because these are inclusive, like, closed intervals and inclusive intervals. And so, yeah, that's basically what we're doing here. But to do this part, we're just counting the index. So it's index times x, that's how many x's we have, minus the prefix sum of the index. And then the opposite here, we're taking the prefix sum of n minus prefix sum of index, which is the suffix sum. And then we're subtracting n minus index times n, or times x. And then lastly, since these are actually all plus 1, plus 1, plus 1, and so on, we need plus n at the end. Yeah, that's it. You just need to make sure you don't do anything quadratic. You use this binary search, use the prefix sums, and then you're efficient. So that's E. Like I said, we'll go pretty quickly. Problem F. You want to find how many pairs I and j satisfy AI plus aj equals x and AI times aj equals y. It turns out this is actually pretty much just solvable. It's a quadratic equation, right? You have a plus b equals x, a times b equals y, and then you can just take the second equation as a times x minus a equals y. This is a quadratic, ax minus a squared equals y, which is also a squared minus xa plus y equals 0. You can solve that quadratic, you use the quadratic formula. It is just x plus or minus the square root of x squared minus 4y all the way to 2. This is, you know, simple high school math. And then that's just what we're doing. We're just doing that. Make sure you don't take the square root of negative number. Make sure you round to an int. Make sure you check that it's equal and make sure that's an int. Make sure that you can actually divide by 2 and still be an int or an integer. And then just do it. And so now we have a and b. So we know the values a and b where they do this. Basically, this plus or minus will give you either a or b, right? It's possible they're equal. If they're equal, we just need to count the a's and do that choose 2. If they're not equal, then we do count of a's times count of b's. The counts are just via this map. I just have this getter function that tries to avoid inserting into the map. In the actual contest, I did, you know, this. The downside of this is that you insert into the map when you're just trying to query, which is still fine for the complexity. It's just a little worse. But anyway, that is F. Yeah, it's very standard basic math. Nothing too exciting or crazy. Yep, and then finally G. Right, we're given a tree, a weighted tree. We want to count how many graphs satisfy basically no self loops, no multiple edges. The weights are integers not exceeding s, and the graph is exactly one minimum spanning tree, which is the given tree. So the key idea here is if a graph has exactly one minimum spanning tree, then any edge that is not in the tree is greater than the path max on the tree between those two nodes. And you can think about this through, Kruskal's algorithm, for example. It has to be not possible to insert that edge. Basically, by the time you get to that edge weight, you've done the edges less than that edge weight. You've already connected those two nodes, so it won't be in that. There's no way the algorithm can include that. But basically here, the idea is then for any pair of nodes that we would consider adding an edge for, that isn't already in the tree, obviously, we can put any weight that is greater than the max weight on the path. And we just multiply all of those together. And obviously you can also not put an edge. So those are the options. It turns out the way to do this, you just sort the edges by weight, and then you just run union find. The reason to run union find is that, okay, here for the first time we are connecting u and v with a weight of w. We just want to know what is the size of u's component and what is the size of v's component. And when we join them here, we're actually going to solve all of the edges that cross u's component and v's component, all of those edges at once. The number of edges there that are possible is a times b minus 1, where a is the size of u and b is the size of v, their components. Minus 1 is because we already have the u to v edge, and we can't add that one, but everything else is kosher. And then the number of choices per edge is s minus, so we had to be greater than w, right? So we have options of w plus 1, w plus 2, all the way to s. That count is s minus w, and then we also have the option of not putting an edge, which is plus 1. And then so we're just multiplying that for each of these pairs, right? So it's just choices to the power of pairs. Multiply that, just unite, and then that's the answer. So yeah, that's it. All these turn out to be pretty simple. All these problems felt like they were very standard this time around. Nothing too unusual or exciting, which is fine. I mean, it's a div 3. But anyway, that's it for this one. I'll see you in the next one.